and start the slideshow from current slide. Okay. Trying to think if there's anything important. The computer's working better. Yesterday, though, worked fine in the morning, in the middle of the day. Toward the end of the day, it started. I think it just gets tired. Okay, so because Monday and Wednesday both, I have early classes all 4 days. Then I have a middle class on Monday, Wednesday, and I have the time open. But Dr. Ellison has started using my computer because it works better with my projector. She's using my room because the room she was in, the projector was stolen. So she's using that room, so I just leave the computer in there. So by the end of Tuesday, it's tired. It's been 2 classes. It doesn't want to do a third one. But today it's doing fine, so knock on wood. So I think we're okay. Any questions on anything we've done so far? None? Okay. All right. Well, where we left off last time, we were talking about the force due to friction. And this book uses a sort of standard, I guess it's nomenclature here. A force is usually capital F. And then the subscript is what kind of force it is. So this is the force due to friction. If you remember, the force due to weight was F sub W. The normal force was F sub N, but that was a capital N. I use a little n for net force. That's not what kind of force, it's just the total forces. Okay, so this is force due to friction is equal to mu times the normal force, F sub N. Okay? Now, that's the force perpendicular to the contact surface. Now, what I was going to explain before, and we don't really need it because we're not doing this kind of problems, but if you had an inclined ramp, the normal force is this way, not the same direction as weight. That's why we don't use weight, we use the normal force. And then you have to break the weight down into components parallel to the plane, which is not part of the normal force, perpendicular to the plane, that would be what is. We don't have to worry about that. We're not doing those kind of problems. Physics students like those kind of problems. Okay, now, about this coefficient of friction, it's the ratio between the frictional force and the normal force. Because you see, you could rewrite this equation by dividing both sides by the normal force. Friction force, the normal force, yeah. These go out, and you see that's what mu is. Mu is the ratio between those two forces. Now, you don't need to know that, but that's how they determine these things. Okay? Now, there are 2 types of coefficients of friction. One is mu sub s for static friction. Remember, that's the friction when you're just trying to push something hard enough to get it going and it's resisting the motion. That's static friction. Okay? The other is mu sub k, which is the coefficient due to kinetic friction. Once it's moving, how much friction have you got then? And remember, mu sub s is almost always greater than or equal to mu sub k. Or you could write it the other way and have mu sub k being less than or equal to. They give a few examples of that in your text. I'm not going to repeat this, but you got your books there in front of you on the top of page 133. Steel on steel, you see static friction 0.58, kinetic friction 0.20. That's less than half. The moving friction is kinetic friction. Steel on steel lubricated, they're almost the same, because now the lubrication prevents any of those little crevices and grooves. They get filled with the liquid, so it just slides right on over it. Glass on glass, again, less than half for kinetic friction from what it is static friction, 0.95 for static, 0.40 for kinetic. Hardwood on hardwood, not quite half, but it's 0.40 to 0.25. Steel on concrete, they don't even give a static friction. I'm not sure why, but kinetic friction, 0.30. Okay? Aluminum on aluminum, they give the static 1.9. They don't do the kinetic. And there is sort of a reason for that. Aluminum is a rather soft metal. So if you have an irregular surface sliding on aluminum, even other aluminum, then what happens when it gets down in those grooves and you start pushing it, it starts digging in. It starts tunneling through it, and it actually makes it higher. So they don't even give one for kinetic friction because it tends to dig deeper into the thing and make it even worse. Okay? Rubber on dry concrete. Now, why is that important? Driving your car. You count on friction keeping you going. 2.0 for static friction, 1.0 for kinetic friction. Rubber on wet concrete, oh my goodness, look what happens. 1.5 for static friction, 0.97 for kinetic. Not a lot better on kinetic, but I mean, when I say better, actually worse because there's lower thing. Aluminum on wet snow, that would be like you're skiing or slaloming, okay? 0.4 static, 0.02 kinetic. That's why those downhill racers can go so fast. Steel and Teflon, man, almost no friction at all. 0.04 for both static and kinetic. Teflon is that really slick material. They started making cookware with it. Now they have Kevlar and other things that are even better, but Teflon was the original there. Okay? So they have a little place, try this activity. You certainly can do that on your own. We don't run a lab in here, so we're not going to do it. But in general, we like to reduce kinetic friction. Okay? There are some times we don't like to. Like when you're driving the car, you don't want to reduce the kinetic friction. That then loses control. You start skidding. Okay? So we want kinetic friction on the road. But on a lot of things, like in your car engine, you don't want kinetic friction. You want that to be as slick as possible, so you're not losing energy to overcoming that. So here are the 4 things they say to reduce kinetic friction. Okay, I'm not going to spell out friction. Okay, number 1, smoother surfaces. Okay, that's why if you, I'm not a skier, so I'm not certain about this, but I believe it's probably true. Especially the old wooden skis. I don't know if anyone uses wooden skis anymore. But what they would do, they would sand them down so they have them just as slick as possible so you could reduce the kinetic friction of the snow. So they can go faster. Me, I just soon have a brake on, okay? So smoother surfaces. Number 2, and this is what we do in car engines and stuff, we use lubrication. The lubrication forms a barrier, a boundary between the 2 pieces of metal. They slide both over the oil, so there's hardly any friction at all. So lubrication. Number 3, use something like Teflon. Okay? To greatly reduce friction between the surfaces when an oil lubricant is not desirable, such as electrical sources. So when you're trying to reduce frictions with something that has chance of electrical contact, you don't want to use oil, okay? Oil may flash, explode, and things like this. You don't want to use it, okay? And then here's an interesting one. I can remember my uncle talking about this when I was a little boy. Use rolling friction. Rather than sliding friction. Okay. Now, notice here, what did I just do? I pushed back in the chair. And it didn't take much effort to move it because it has rollers here. If I had pushed back in this chair, that's more effort. You can hear it grinding on the floor. Even though this is pretty slick, that's pretty good. It didn't do too badly, but rolling is much better. See, rolling friction, there is immediate friction right there when you're touching the surface, but then it rolls right on past it. So you overcome those crevices in the floor, you roll right over them. And in the wheels too. So usually a good idea, yes.
What they do, like with some of the patients that can't walk and walk on walkers, they put
tennis balls.
Tennis balls.
Yeah.
Reduces them from having to push so
Exactly, exactly. And that's exactly what it's doing, reducing the kinetic friction. Excellent example, excellent example. Okay, so here is their first example, example 1. Okay, bottom of page 133. A force of 170 newtons. We don't know what kind of force that is now. Is needed to keep a 530, I can't read very well, 530 Newton wooden box. Ooh, goodness. Okay, I have to check and make sure every time I do that it doesn't mess up my power. Okay. To keep a 530 Newton wooden box sliding on a wooden floor. What is the coefficient of kinetic friction? Whoops. I did everything backwards here, okay. Let me erase that. I put the K, which is for kinetic, I put that as on the main line and put my subscript, I was going to put the mu down there. Mu sub K, this is what we're looking for. Okay, now, I don't know if a picture is helpful. I think it might be. Oh, they do show one in the book, but it's not on the slide set. So what I'm going to do, now that I think about it, I should have thought about it sooner. I'm going to go back a slide. To this one, okay? Bring that one back up. Okay, this is not for this problem, but it's similar. Okay? Here is your effort force, okay? Let me write it again. This is now what we're calling the effort force. And I have to use this color now. The effort force, I'm going to call it F sub E for effort, okay? The effort force is your 170 newtons. That's the pull or the push that you have to do on the box to get it to move. And it's a wooden box, and that looks like a wooden box. Sliding on a wooden floor, so we know this is wood down here as well. Okay? What is oh yeah, where to keep a 530 Newton wooden box. Now, what is that 530? What is that? The 500, if I could write, and 30 newtons. What's that a measure of? They say a 530 Newton box. Sort of like saying, I'm a 218-pound man. What you reckon that is? Weight, exactly. This is the force due to weight. So this is the force that gravity is pulling down on this box. That's your 530 newtons. But we're really not interested in the weight, though it's very similar, because if it's pushing down on the floor with 530 newtons and the floor is not giving in, that means the floor is pushing up with 530 newtons as well. That's then your normal force. Okay? And it seems silly to call them two different names. They're the same value, but one's pushing up, the other's being pulled down. But they're the same thing, meaning it's not floating up in the air or crashing through the floor. They have to have the same value. Okay? Well, then what was the relationship between normal force, frictional force, and that, by the way, this is the effort to keep it moving. That means your frictional force, if it's not accelerating and not increasing speed, that means the friction force is also 170 newtons. So you see, your effort force, if it's moving at a constant speed, has to equal your friction force. Because unless you have it accelerating, then the effort force would be greater. But if it's not accelerating, it's just keeping it moving, that means it's at the same speed, so the friction force must be equal to, because the net force is zero, because you're not changing its velocity. Okay? Not changing its velocity. So both of these, the effort force is 170, but that means the friction force is too, since it's not accelerating. The weight downward is 530 newtons, but guess what? That means that the floor is pushing up with a normal force of 530 newtons. Now, the question is, what is the coefficient of kinetic friction? What did we just say it was on the previous slide?
On the previous slide?
Yeah, one of the ones earlier, when we were talking about the formula here. The coefficient of friction on the previous page, that last paragraph, next to the last paragraph, the coefficient of friction is the ratio of the frictional force, that is 170. It's the ratio of the frictional force to the normal force. Remember, I had that on the slide before. I've already erased it so you can't see it, but so this will be 170 newtons divided by 530 newtons. And notice the units cancel out, which means your coefficient of kinetic friction here is a dimensionless quantity. There are no units with it. So don't put any units, okay? Pull out your handy-dandy calculators and see what 170 divided by 530 is.
3,000.
Oh, wait. I think you divided the wrong way. 170 divided by, you multiply.
I divided 5 into
170 divided by 530.
equals 0.32.
Say 0 point what? I can't hear.
0.32.
32. And it has no units because it's a dimensionless quantity. How did the book do? Let's see. 0.32. Good for them. Okay. Notice that mu does not have a unit because the force units cancel out. Now that leads to another issue. If you're measuring the frictional force with one unit and the normal force of the weight with the other unit, you got to get them in the same units first, so your units will cancel out when you get your mu. Okay. Now, there is another blurb here, pretty interesting one, about friction and anti-lock brakes, and that's exactly what anti-lock brakes do. They sense when you start to slide, when you go from static friction to kinetic friction, start sliding on a wet road or icy road or any kind of road, and when that happens, then they release it until they get back to static friction case. And they do it automatically much quicker than you can, so that's a pretty interesting little read. Well, we just finished 5.4, so homework exercises here, do any of the odds 1 through 7, and do any of the odds 9 through 15. Okay. And then they have another little blurb there, new technologies, on hydrophobic metals as one way to reduce friction. And that actually, I think, is what they're saying Teflon is. Okay? The egg will slide right off the pan. It won't stick to the pan because Teflon is a hydrophobic metal or substance. It's not really a metal. And this is showing a hydrophobic metal with a water droplet. The water doesn't coat the metal. It tries to get as far from the metal as possible. So that's what they mean by hydrophobic. Phobia meaning fear of. So it's like the water fears the metal and tries to get away from it. Okay. Good deal. Any questions on 5.4? All right. 5.5, total forces in one dimension. Okay. I think I'd better go to the other slide. Okay. They usually stay open, but they're not doing it now, so I'm having to open them every time. We'll go back from the current slide. Okay. What they say here, when forces act in the same or opposite directions in one dimension, okay, so that means they're both heading in this direction, side by side, one after another, whichever, or opposite directions. As long as that's one-dimensional motion there, that's what we're talking about here, okay? The total or the net force can be found by either adding the forces if they're in the same direction or subtracting them if they're in opposite directions, okay? And it says it's often useful to draw the forces as vectors because that's exactly what they are. So here we have two guys pushing on a, looks like maybe a filing cabinet or a big old cabinet of some nature. The bigger guy's pushing with 175 pounds. Now, I can't draw nearly as well as the book does, so y'all both got your books, so I'm going to let you look at those. I will do the force diagram, and that's much easier to draw, okay? And I like to do it this way. One guy is pushing. Now you notice, you say, wait a minute. These two guys are pushing on different parts of the box. It doesn't matter. We can use what they call the center of mass, just some point in the middle of the box, and treat all the forces as acting on that one, and you don't have to figure out where you're pushing on the box. Okay? So that's what that dot stands for, the center of mass, you might say. Okay? And you treat all your forces as you're coming from there. So here's the big guy pushing with 175, and was this pounds? Yeah. So we're back to U.S. customary units, whereas the little guy is pushing with, pretty well. He's pushing with 150 pounds of force. Okay? Now it says, find the net force exerted. Okay, that's pretty easy. What would that be? The net force would be force 1 plus force 2, or force big guy versus force little guy, small guy, okay? All right. They're acting like they're working hard anyway, okay? So what would this be? This is really easy. What's the net force on the box? Yeah, 175 pounds by the big guy, 150 pounds by the small guy. Okay, except that you didn't carry your 1. It's 325 pounds. Right? Net force of 325 pounds. Trying to lead me astray. Oh, and where is it going? We treat them as vectors, so we also need a direction. The way I drew it, to the right. Okay? The way the picture shows, they're going off at an angle, sort of, but I don't care if it's sort of more to the right. Okay? Now, The same two workers push the crate to the right, and the motion is opposed by a static frictional force of 300 pounds. And of course, static friction always resists the motion. So that would be 300 pounds to the left. That static friction, well, I probably should just put F, and that would be 300 pounds. I'll put a bar over it. Now, they didn't put a bar over the one. Yeah, they did. I just didn't see it. Old cataract is messing up with me again. Okay. Oh, and I guess I ought to go on and say this now. Next Thursday, 1 week from today, I have the cataract. This one, I have the cataract removed. So that means I won't be here. They don't want me driving or doing anything else that day. So, yeah, I don't know. They haven't called and confirmed when, but they told me when I saw the, when I had the eyes checked, they set me up for next Thursday. Is this yours? I just happened to see it. Okay. So, next Thursday, save yourself a long trip. Okay. Now, if I find out something different, hopefully I'll know by Tuesday. Second?
It's the 13th or the 20th.
Oh.
13th or the 20th.
13th. Yeah, the next Thursday. Today's what is it? 6th? Yeah, next Thursday. Yeah, I'll be here Tuesday. Yeah. Blind as bat. No, I'll be here Tuesday, but I won't be here Thursday. Now, I'll know Tuesday. Hopefully, they will have gotten in touch with me and told me my schedule. If they say, oh, sorry, we're full up Thursday, we're going to have to wait till next Thursday. If they do that, then I'll let you know Tuesday. But hopefully by next Tuesday, I'll know. So I can tell you, yes, for sure, I won't be here. But just for planning purposes, I don't think I'll be able to come in.
I'm going to call your wife and I'm going to call the president and everything. Say, keep him at home.
Yeah, actually, my wife will be keeping me at home. She's all right. In fact, we pushed it off. They were going to schedule me for tonight, but I have my 50th high school reunion coming up this weekend, and my wife said, no, you don't need to be going on a long trip. You don't need to be out among people. You need to be keeping it.
That's a smart wife.
Well, she married me. She can't be that smart. Okay. All right. Now, so here we have a frictional force, same box, same worker, same push, but now they have a 300-pound frictional force pushing it, in the opposite direction. Okay. Now the question here is, where is the question? Oh, find the net force now. Same two forces to the right, but now we have one opposite it, so that would be to the left. So what's the net force now?
25.
Yes, you're absolutely right. Subtract the 300 pounds to the left, and that leaves you with 25 pounds in which direction? To the right. To the right. Right. That's one of those line dances. Okay. Now, guess what? Your static friction can never exceed, and this isn't static friction, by the way, that would be kinetic friction, because if it's greater to the right than it is to the left, that box is going to move. It's going to be accelerating. So I really question whether that was static friction or kinetic, but we'll just let them get away with that. Okay. Make sense? All right. Let's go to example 3. All right. Same box, same guys, same everything. The crate in example 2 has a mass of, can you believe this? They gave us a mass of 5.00 slugs. I don't even know how heavy that thing is. It sounds like a sort of small number, but a slug may be a big unit. I don't know. No one uses slugs. What is the acceleration when the workers are pushing against the frictional force? Well, this is now what we call the net force, 25 pounds to the right. The question is, what is the acceleration? We know the mass. We know the net force. What formula do we use here?
Multiplication.
Say again?
Multiplication.
What formula? Always let the formula determine what operation you're going to do.
The pounds. Acceleration.
Say again? Yeah, it has acceleration. Yeah, that's like I should have written that down. What is the acceleration? This is the unknown. What formula relates force, mass, and acceleration?
Force, mass, weight.
Okay. Weight is a force, but that's not really in the picture here. What formula relates a net force, a mass, and acceleration? Think Newton's second law. We did a bunch of them before we did the weight ones. Remember that? Is F, net force, is equal to mass times acceleration. Remember that one? Yeah, that's the one we use. That relates all three of these things together. Of course, we're wanting to know what acceleration is, so what would that be? You would divide both sides by the mass. So acceleration would be the net force. Remember, use your little triangles or circles if you want to. Divided by mass. And what's our net force? .25. Now, here it says pounds. I don't know if you remember this one because no one ever uses it. What is a pound? A pound is a slug foot per second squared. Just like a Newton is a kilogram meter per second squared, a pound is a slug foot per second squared. Divide this by the mass, which we saw was, I wrote down 20. Where I got 20, I have absolutely no idea. Okay, that's 25 pounds. Okay, or 25 slug feet per second squared. Ah, here she is. This is Brianna. Okay. Now I'm hoping by next time I have your names in my grade book, but this has been a panic week. I think I may have told you this before. Last Friday was my last Friday over here because we don't work Fridays anymore. For June and July, we'll be back on campus on Fridays in August. But last Friday was the last Friday in May, so we were working. I was over there on the Birmingham West campus and waiting, and secretary showed up after a while, but my boss never showed up. I said, well, is Dr. Pruitt coming in today? They said, oh, he's in a meeting somewhere down out of town, you know, some sort of instructional officers meeting or something. I said, well, isn't it time we do contracts? And she said, he hasn't said anything about contracts. I don't think it. They would have said something about, no, we haven't heard any word about contracts. I said, well, fine. Okay, we'll wait till next week then. Well, then, either Monday or Tuesday, here came the email. Contracts are due tomorrow, you know. And if they'd have just let us know, we could have run all the information on Friday and gotten it done. But no, they had to put it in panic mode. So this week I've been trying to, in between classes, try to get the contracts done. And I just delivered them today before I came. That's why I was on campus early. Say 25 slug feet per second squared, that's what a pound is, divided by 5, and it's 5.00 slugs. Now here's something we haven't done here. And maybe it's a good idea. Notice when we added the two guys together, we had 175 pounds and 150 pounds, with the zero being significant. Those all three digits are significant, so 325 pounds, that was significant. Okay, so we keep the units. Then when they told us the frictional force, they said static friction, but I really think it was kinetic. That was 300. They put the bar over the second zero, meaning all three digits were significant. But then we did a subtraction. When we subtracted, we lost a digit because the threes didn't, they subtracted out. Do you put another decimal here? No, you don't. It's only when you're multiplying or dividing that you have to keep the same number of significant digits. When you're adding or subtracting, when you add another digit, you can only go to the nearest precision. So this is to the nearest pound, to the nearest pound, that's to the nearest pound. Suddenly you can't go to the nearest tenth of a pound. No, you don't have that kind of precision here, so you can't go to it here. Adding and subtracting, you don't keep up. So what we've got here is two significant digits divided by three significant digits. There it is. Three significant digits there. Guess how many significant digits you're going to get out of this one? Now we're dividing. What would that be? I can do 5 into 25. That would be 5, right? But you have two significant digits. 5.0, what unit? Feet per second squared. Because the slugs canceled out. Okay? Now, did they do it in the book, right in the book? Yes, they did. 5.0 feet per second squared. Great unit for an acceleration because it's a distance divided by time divided by time. So that's your acceleration, 5.0. And that's why there's only two significant digits, because even though the mass was 3, the net force was only 2. Because when you subtract those two 3s, you can't throw in another. You didn't make it any more precise. You're only good to the nearest pound. Okay? But here you're good to the nearest tenth of a foot per second squared. All right. Now, there's one more example here. And this is example 4, and it's similar to the the last two, but not the same. Actually, the last 3, but not the same. So I'm going to go to a clean slide. It's going to be very similar, but not quite the same. Oh, I'm sorry. I should have asked first if you needed that any longer. I can't retrieve it, so too bad I hope you got it. All right. 2 workers push in the same direction on a large pallet. The force exerted by one worker is 645 newtons. Boy, that's a hunker. Okay, so here he's doing 645 newtons in this direction. I'm going to, again, just do a box here and let that be my pallet. Okay. The force exerted by the other worker is 755 newtons. Even bigger. So this is 755 newtons. See, we're in different units now. The motion is opposed by a frictional force of 1175 newtons. I should make that even longer. 1175 is the force due to friction. Newtons. Find the net force. Very similar to the last problem, just different numbers. What would you do? Add the two together, and what do you get? I think it's 14, isn't it? 1,400.
I don't know, I'm just off today.
Yeah, me too. Okay. 1,400 newtons. Now, here's another interesting issue in significant digits. This is actually good to 4 significant digits because those two are to the nearest newton. You're just adding them together, so that's to the nearest newton. So now you got 4 significant digits there. Not 3, but 4. Okay? The motion is opposed by a frictional force of 1175, so what do you do with that? subtract the 1175. Okay, and when you do that, you get 25 here, 225 newtons. Back to 3 significant digits, but that's perfectly fine. All right. That was a pretty easy section there, wasn't it? Okay. That's problem set 5.5. Do any of the odds, I'd say 1 through 5, and then do either 7 or 9, and either 11 or 13. Okay? All right with that one? Okay. Now, how are we doing on time? Oh, yeah, we got plenty of time. All right. Can I erase this?
Yes.
Okay. So what I'm going to do is actually leave this one and go back to this one. Okay, go down one slide, and this is what we're going to be doing now. All right. 5.5, or 5.6, I can't read. My cataract. Okay, I'll blame everything on the cataract. I don't know what I'll blame it on in 2 weeks, but I'll blame it on the cataract now. I'll blame it on the surgery then. Okay. Oh, and by the way, it was before you came in, Brianna. Next Thursday, I'm having cataract surgery on this eye, so I will not be.
I won't either.
You won't?
My birthday falls on Father's Day, and I'll be out of town.
Oh, you will? Okay. Well, you timed it well. Okay.
No, it was already pre-planned.
Yeah, I know. This was pre-planned too, but I just hadn't told you yet. Yeah, so I planned it well then. I'll say it that way. No, they've scheduled me for surgery. Now, if something changes, I'll let you know Tuesday. But right now, plan for, I will be here Tuesday, knock on wood. But Thursday, unless something changes, I won't be here. So you don't miss class then. Okay. Now, we'll talk about this on Tuesday. Do you think you want to just use videos that are already out there? Or do you think you want to me to pick up where I leave off Tuesday and the following Tuesday? Pick up? Okay. All right. All right. That's just one issue. There's another one coming up real soon, but we'll talk about that when we get there. 5.6 is talking about the law of action and reaction. When an automobile accelerates, now notice that word, accelerates. That means that it's moving, there's the net force in this direction has to exceed the force in that direction. The net force has to be non-zero for acceleration to happen. Okay? So, when an automobile accelerates, we know that the force being applied to it, a net force is being applied to it. What applies this force? You may think that the tires exert the force on the auto. It's really the other way around. This is not correct because the tires move along with the auto. There must be a force applied to them also. The ground supplies the net force to the tires. The tires are trying to turn, the ground's holding its own, and that pushes the tires in that direction. Believe it or not, the ground is supplying the force. Okay? That force is called a reaction force by the tires on the ground. The tires are pushing on the ground pushes back. Tires pushing on the ground, that's the action force, and this is Newton's third law of action and reaction. For every force applied by an object, A, to an object B, okay, that's the action, there is an equal but opposite force exerted by object B on A, that's reaction force. Now, understand that maybe Newton did something like this when he was describing it. I don't have a rock in here, but if you imagine this is a rock, and I'm going, well, that moves. Okay, well, let me get something that doesn't move, like this corner here. I'm going to push against the desk here. And I'm pushing pretty hard. Guess what? It's pushing back on me. See the indentation in my finger? It's pushing back on me. For every push that I do there, it's pushing back. equal and opposite. Now, how does this differ from the first two laws? The first law, when an object is going to be either at rest or in motion unless it's operated on by a net force, an unbalanced force. That's the first law, the law of inertia. It's going to maintain its motion, whether it's at rest or moving, unless it encounters an unbalanced force. Well, guess what? If there's a force involved, that's on that one object. Okay? Newton's second law is the one we were talking about earlier. If an object does accelerate, change its motion, change its velocity, that's an acceleration, that means there had to be a net force on it. Well, that's on that object. And both of those, the only forces involved are on that object. The third force, you've got two objects. You've got the finger and the desk. Or Newton said, pushing on a rock, the rock pushes back on my finger. And that's two different objects. And so the force that your finger exerts on the rock is equal to the force that the rock exerts on the finger. Now, this is not an illustration of action-reaction because they're different. What this is saying is that the net force this way of the ground pushing on the tire is 500 pounds. The frictional force that's trying to retard that motion is only 100 pounds. So this is going to be a net force of 400 pounds in this direction. Okay? That's not action-reaction. Action-reaction, the tire is pushing on the road with a certain amount and the road's pushing back on the tire. That's action-reaction. And that's what the net. This is all based on the car. The car is being pushed here, being pulled back there. The net force is 500 pounds. Because you're always only talking about the forces on the car. Okay? The action-reaction force, the tire is pushing on the road's pushing on the tire. Two different objects. Tire on road, road on tire. Okay? That would be your action-reaction force. Okay? And this is not the slide. Okay? We'll get to that in a second. This is the slide that's the action-reaction force. Yeah. Okay? I'm getting stuck on my badge here. When the ground supplies the force to accelerate the car, the tire pushes on the ground pushes on the tire. Those are action-reaction forces. The ones up here, both of those are acting on the car. So that's net force, 400 pounds in this direction, okay? Because all those forces are acting on the car. This one, the tire's pushing on the road's pushing on the tire, that's action-reaction. Two different objects, equal and opposite forces, always, okay? And that is Newton's third law. Now, that leads then to the next illustration, and that's this one. I don't know if you've ever fired a weapon before, have you? Okay. All of you?
No.
No. Okay. I hate firing pistols. Pistols are so incredibly inaccurate. But I was the gunnery officer on my ship, so I had to be qualified to handle weapons. We fired into the ocean, so I wasn't about to hit anybody. But I had to know the safety and stuff. But when you fire, what happens?
Jerk back.
Yeah, it's always jerks you back. And that's why it's incredibly inaccurate. Okay, well, it's a short barrel, it's hard to judge. And then if you fire a second time, probably it's going to be up in the air somewhere. So, terrible idea of firing a pistol. Okay? Now, the action of the bullet, the bullet is being pushed by that explosion out of the barrel. That's the action. The reaction is the barrel is pushed back against your hand, and that's what makes it jerk. Now, I far prefer, though I don't like shooting anything, but I far prefer a rifle. But if you've ever shot a rifle, the rifle you better snug up against your shoulder. If you don't, if you hold it off your shoulder, you're going to have a bruised shoulder. And if it's really high-powered rifle, you may even have a separated shoulder if it hits it just wrong, because that is a pretty significant reaction force. Okay? Therefore, you held it snug up against you, because the same force with which the bullet's being exploded out of the barrel, that force is back on you. But if you're snug up against it, now it's not just the rifle mass, it's your mass and the rifle mass, and it's a lot less. So that's why you hold it tight against you. Otherwise, you have a bruised shoulder or separated shoulder. So pretty significant, but they're equal forces. And if you think about that little bitty bullet and how much it's accelerating, that's a lot of force. And that's why it jerks back every time.
It's when a jerk, between the jerk and the rifle,
right.
That jerk right there is almost worse, because it takes you.
Absolutely.
Depending on the power of it. Like when I put the rifle on my arm and
Yeah.
I go to shoot,
Yeah.
and it's snugged up against me.
Right.
And
See, you're part of the system then. Here, it's just, it's just your arm. That's the only thing you've got, and it moves it. But when you got it up against your body, you got the whole body against it. You still move a little bit, but it's not nearly as much as a, yeah. You're absolutely right. Now, that leads to another pretty interesting little, they have it as an activity here, but let me just give you an illustration of it. What they have is a setup where you have a wire, okay, pretty tight wire, and you have a tube that's, the wire is going through the tube, and strap a balloon to it. You've blown up the balloon, but you just hold the end down and then release the balloon, and it just takes off and goes. Well, what you have is action-reaction. What you have is the air rushing out of the balloon, and that pushes the balloon forward. And that is basically the first propulsion we had, okay? Now, when you just release a balloon, you blow it up and release it, it just sort of goes all over the place. Well, the reason for that is, where's the air going out? It's going out that little nozzle, and it's a floppy nozzle. So when it goes this way, the balloon's this way. When it goes this way, it goes that way. It goes like the proverbial chicken with his head cut off. It just goes in all directions, you know. But when you have it guided on that, then it pretty much has to go along the wire. Okay? Now, so balloons were the first flight vessels, as in blimps and things like that. After that, they got propeller planes. What a propeller plane does, the propeller has a certain cant to it, and as it turns, it's taking air and pushing it back. Okay? And that's what propels the plane forward. Again, action, reaction. That's why the plane goes forward with a propeller. Then they came up with jet planes. Well, jet planes, you don't have a propeller pushing the air back. You have the exhaust from the jet engine firing out the back, and that pushes the whole plane forward. Action, reaction. It goes at really high speeds, you know, that propeller, the exhaust gas. And then the third type, the next type, is a rocket. And that's what they show on the next page. What's going on there, it's sort of like a jet engine pushing down, and that pushes the rocket up, but in a sense, that's far more like your balloon, okay, than the other two. So we've almost gone back to the balloon technology. Okay, and that ends the chapter. Okay, now one thing I didn't look ahead. Well, I had all these other things, the contracts and stuff to do, so I didn't get them done. I have your tests made out, but I don't have them copied. So what I need to do is before, I'll take that back. I have enough copies for you guys. Now if I, oh, here it is. Haley comes in. I'll have to go make a copy for her, but I have 3 copies now. So since y'all are here, I will give these 3 copies to you. Let me make sure this is, yeah, okay. And I'm going to assume our fifth student is just not going to show. Can't remember her name now, but it was Addison Gray Nelson. No one's seen her or heard from her. I shouldn't say this, but she hadn't paid, so I guess she's not going to, so she's probably not coming. So there's the first test. Now you'll notice there is a correction on it, and I found this test bank to be pretty woefully poor. Number 7, using the number they gave, 17,500, it wouldn't even pull them. Okay, so you were in serious trouble. So I went to the answer, worked backwards, and found out they had just left off a decimal place. So it's 175,000 pounds of pulling force. Now it will work. Okay? Now, I'm giving you this today. Technically, it's not due until a week from Tuesday. Because remember, I always give you a week so you can have one more day to ask questions, like next Tuesday. But since we're not going to be here Thursday, Tuesday would be the earliest. Now, if you finish it and you want to turn it in Tuesday, that's fine. But if you do want to ask questions or other things, now, the questions I can answer are things like, what do you mean by this problem? What are you really asking for? That kind of thing. The question I can't answer is, how do you work this problem? That's why it's a test. That's for you. But what you can do is find questions like this in the text. I'll work anything from the text. So even if it's almost identical, not identical, but almost identical, I'll work anything in the book. Even, odd, or whatever. If you find one like these in the book, if you don't know how to work this, find something in the book, and then we'll work those in class, or by individually or whatever. So this is the test on chapter 1. Still got to make one more copy, and y'all need to remind me to do that when I leave today, okay? I have a good memory, it's just short. So let me remember to make a copy. Because this finishes the chapter. There is a glossary at the end that gives some of the key terms, okay, which is well worth noting. There's a formula sheet, 3 formulas. Excellent to look at those. You probably will use those with a couple of your constants. There's review questions, which are pretty good to get the concepts down. But then the review problems, those are far closer to what you'll see on your test and what your other homework has been. So if you do need a few more to practice on, the odd numbers 1 through 17 would be other good ones to practice on. Okay? Then there's applied concepts. You can read about that if you want to, but don't sweat that too much. All right, so that was chapter 5. I've just given you the test on chapter 5. The next chapter we cover, we skip momentum, which is a great concept. Concurrent and parallel forces, we're skipping that one. That's chapter 7. And now we finally move to chapter 8. And this is based on the course description, which is what they came up with when they developed the program, and said you need to know about forces, you need to know about work and energy. Forces is chapter 5, work and energy is chapter 8. So we're going to move to chapter 8. So let me get out of this.
What time do we get out of here?
6:30.
I'm gonna be up picking up.
What's that?
I don't know. I told you I've been feeling kind of ill, so
Right.
I done packed up. I'm ready to.
Just because we finished the chapter. No. I gave you that so I wouldn't forget it at the end.
Okay.
All right. So let me find
Chapter 8.
chapter 8. There we go. Here we go. Moving on to chapter 8. All right. All right. Now, Chapter 8 is talking about work and energy. Do those seem related to each other?
Yes.
Yeah, they certainly are. In fact, they're so closely related, their definitions almost overlap. Work is changing something's energy state. Energy is the ability to do work. Hey, they're so closely related. Guess what? They even use the same units. And we'll talk about units a little bit later. Work is just another form of energy. Energy is just another form of work. Okay? Now, what is work? That's the first question they have here. And the first slide is not for several pages away. Okay? So let's go back to the this one, and we'll go from this slide. Okay. Now, I'm going to give you a little story. This is a true story, sadly. Okay? Well, I really ought to give the definition first, so I think I will. Hold on. On page, I can't see the page number here, 201, page 201, says, what is work? Okay? We often associate work with physical or mental effort that leads to fatigue. The technical definition of work is much more limited. Okay? If we try to lift a heavy crate, but it doesn't move, we would probably say we've worked because we strained our muscles, we grunted, we sweated, we may have said some bad words, whatever we said, but if we didn't move it, we did no work. Because what work is force times a displacement. And even though you may put an awful lot of force into it, if you don't move it, you've done no work. Sad, but true. Okay? The picture they show at the top of page 202 of the one guy yanking and pulling and doing everything he can, but he can't move the box at all, the crate, he's not doing any work. No matter how much he's sweating, how much his muscles are hurting, he's doing no work. The second guy, though, or the same one that finally got it moving, he is doing work. Okay? Now, here's my dumb story. True. When we were looking to move from the house we used to live in to the one we live now, we were in a little two-bedroom bungalow. We liked it. It was a great house, only one bath, 2 bedrooms. But when a lot of family came by, we were sort of stacked in there. We had a pretty good-sized living room. We could sleeper sofa. We could do that, but still the bathroom, one bathroom, pretty tight. So once we were doing pretty well on getting that, I'd gotten a job that was doing a little bit better. My wife would offer she started as a grad student, so she wasn't making hardly any money at all. Then on fellowship, making a little bit. Finally, when she got as an assistant professor at UAB, she finally started making some real money. I had been working at UAB as a programmer, doing okay, but not doing great. Then got a job at Southern Research, doing a lot better, and then ultimately I got the job here, which did a little bit better than Southern Research did. So we finally were able to afford a little bit bigger house, so we went for quite a bit bigger house, and we went to a neighborhood that she really liked. And the only bad side, though, this house sat up on a hill, kind of. And it was here, but the hill kept going up here and coming down here. They had leveled off and built the house here. But then some subsequent owner had decided to build something in the back part of the house. So he had to dig into the hillside sort of to put a family room and a screen porch. And by doing that, now the soil level came right up to the windows, and they were little squatty windows, okay, because he built into the hillside. Well, I looked at that, and we liked the house. We really liked the house. It was a good house, pretty solid. But I said to Karen, you know, if we do get this house, we're going to have to do something, because you see all that water that comes off that hillside is just going into the back wall of the house. And that's going to create a hydraulic pressure on the wall. Number two, I couldn't see where the wood ended and the ground began. It looked like we were awfully close to having wood-to-ground contact. That's not good to have in the South because of termites. Okay? Now, sure, it was fairly recent construction, so I'm sure they used treated lumber, which would be resistant to termite as long as the treatment stayed in the wood, but that leaches out over time, especially if the wood gets wet and stuff. So I said we need to do something about getting the soil away from the back of the house and create a berm or something to run water on either side of it. And then Karen said the words that I dreaded to hear. Good. I wanted a patio anyway. Whoops. A lot bigger job than and we had bought the house by this time. And I had told her again. And she said, good, I wanted a patio anyway. Well, this meant a lot of digging. Not just creating a berm and getting soil away from the house. It meant digging out a lot. Whew, much more than I had planned. That was my first year of teaching then it was Western State Technical College. And that summer was coming up. And, you know, enrollments generally less in the summer. I was a new kid on the block, so therefore I didn't get a full load. I just had 2 first 5-week courses, mini-term courses, and then the second 5 weeks I was completely free. So that's when we decided it was time for me to, and since I was part-time, I only came to 2 days the classes met. So I had, I don't remember, Monday, Wednesday free, but Tuesday, Thursday I taught. And then it was only for half a day, okay? So anyway, I was had a lot more time on my hand. So that's when we started digging out the patio. All right. Now, in the process of digging out, if you've ever done very much serious digging anywhere in the Birmingham-Bessemer area, you know you're going to run into rocks. At some place, you're going to run into rocks. And we did. I did. It was plenty of rocks. I also ran into a few roots, so I started adjusting the dimensions of the patio a little bit. And I really did a smart move. She had taken a hose and said, this is about where I want the patio to be. Boy, it went way back into that hillside, you know. Ooh. So I said, can you help me some on weekends? She said, well, sure, of course I will. When she started digging, she said, let's bring that hose in a little bit, okay, which was I was all in favor of. Okay. So anyway, I was out there sweating and doing, and every now and then ran into a rock, and most of them I could work my way out. But somewhere just about the middle of the patio, I hit something. And I kept trying to dig around it, and it just kept getting bigger and bigger. And I kept digging around it and digging around it, and finally I got around it. It was not a rock, it was a boulder, okay? I mean, that thing sat about this tall where I dug down to here. It had been completely covered by soil before, so I didn't know it was down there, okay? And it had been just below the soil level. I didn't know it was down there, and it was at least that big around and standing there. And when I finally got it all dug around, I started trying to move that thing, okay, because that was right in the middle of where the patio was going to be. And I got cheater bars and levers and rocks under here, and I pried and I grunted and I dug and I did everything I could think of. I could not budge that rock. Was I doing any work?
No.
No. Oh, if you had told me that summer you're doing no work, I would have wanted to do something, okay? But physics says I was doing no work on the rock. I'd done work moving that, but doing the rock, nope, I had not moved it at all. So no matter how much my muscles hurt and I sweated and I grunted and everything else, if it didn't move, I had done no work. So there's my dumb story. Okay. Now, these examples, they also show one hammering a nail, okay, or driving a spike into the ground, or whatever. Given that big old sledgehammer, all the force you can do, and that thing, if it moves into the ground at all, you're doing work. If it doesn't, you're not doing any work. Sort of another story, when we built a house on our farm in Georgia. That's where we're going for my reunion this weekend. And it had been so hot and dry for years. They had had a multi-year drought. And that hillside, where it's a beautiful view, pecan trees in front, and across the road is Scott's Lakes, we call it. It's, tree. You only see two of them, but you see one really nicely. Just a nice view. My wife loved it. That's where we decided to build the house. We laid out the thing, and then my brother and I went to, because it was in the middle of a cow pasture, we needed to put fence around it so the cows wouldn't be in the yard, okay? So we went to drive the metal post into the ground, and I swear we were going nowhere, okay? They were inching down. So what we had to do was dig out just a little cup, and that was hard to do, of soil, and pour water on it and let the water soak in. It was hard clay. It took forever to soak in. So we went around and did every place we wanted and dug out a place, poured water, and then came back and tried to do when we couldn't. We'd pour more water, and finally we were able to drive the post into the ground. And that reminded me of driving this spike into the ground. It doesn't go far, but if it goes anywhere, you've done work. If it doesn't go anywhere, you haven't done work. So here is your definition for work. Work is equal to, let me get my pen set up. Work is equal to, now this is not weight. Sometimes I use weight as little w. Our book uses F sub w, but this is work. Work is your force times a displacement. Now, they use S for displacement. I like to use D, and you'll find me putting D's up there. That means the same thing. They use S. That's perfectly fine. So the work is the force times the displacement. Now, here is the catch to it. If I push on this chair, I move the chair. Well, the force I push times the distance it moves, that's the work I did on the chair. But I can push with that same amount down this way and hardly move it at all. Maybe a little bit, okay? But I pushed a lot harder. Why? Because, you see, this force is not in the direction of the motion. The motion's that way, but my force is this way. So work has to be force in the direction of the motion times the motion. Or motion in the direction of the force times force. It doesn't matter which. But this is, all the force I'm doing here is creating work. Here, part of that force is just pushing a chair into the floor. That's not doing any work. So work has to be parallel to the displacement has to be parallel to the work, to the force. See, force and displacement are both vector quantities. They have directions of them. So if I push down like this, then there's a component of my force that's downward, that's not doing any work. Only the component, which is less in that direction, is doing work. Okay? And we'll get to some examples like this a little bit later. Okay? So, that's why they put the caveat in there, force applied in the direction of motion times the magnitude of that displacement. Okay? Now, what are the units for work? What's your unit for force? You've got two of them depending on what system of measurements you're doing. What are your units for force? Anyone know? We just did, say again? Units for force. Units are important, sort of be familiar with them. We just did a couple of problems at the end of the last chapter. One was, okay, that's the symbol for it. What units is it? So many, like 10.
Come to the second power, the tenths.
What's that?
Like 10 to the second.
Okay, yeah, okay. Those would be the numbers. What unit goes after that number, if you're talking about a force? Let me give you some example. Say again? Pound. That's the force in the U.S. customary system.
Okay.
What's the force in the metric system, SI system? Named after Sir Isaac. Okay, pounds in the U.S. customary system, this would be newtons in the, remember one of the last problems we did was, remember the two guys pushing on the crate? The first example we had that was in pounds, the second one, it was in newtons. One was 600 newtons, one was 700 and some odd newtons. It came out. Huh? No, okay, that's the formula. The units are newtons in the SI unit, pounds in the U.S. customary. Okay? How about displacement? What would we use to measure displacement? The standard unit for displacement in either U.S. customary or SI metric.
Pounds.
No, displacement, distance. What do we use for that? Say again? Distance. What's a good distance measurement? U.S. customary, the standard is feet. Okay? In the U.S. customary, in the SI, it's meters. Meters per second squared, remember? That's acceleration. So the work unit is either a Newton meter or a okay, we write it as pound feet, but we usually give it as foot pounds. Have you ever heard anyone talk about so much work in foot pounds? That's what we got, foot pounds. Okay? Now, that's all we have in U.S. customary, foot pounds, and that's what we call it. However, in the SI system, a Newton meter has its own name. And you gals might like to remember this one. A Newton meter is the same as a joule. Y'all like your diamonds, don't you? Okay. Joule. It's not spelled like that. It's spelled Joule, named after James Prescott Joule. He was a British scientist, a really great scientist and engineer who did a lot of the early work with force and energy and work, so they named the unit for energy after him. Now notice if it's named after a person, it's capitalized. Feet is not named after anyone, that's not capitalized. Pound doesn't even start with L, that's not capitalized. Meter is not named after anybody, that's not capitalized, but Newton's named after Sir Isaac Newton, Joule's named after James Prescott Joule. Now, a little bit interesting story on Joule. Okay, this was back a long time ago, okay? Back when Europe and England were still sort of in their feudal stages. I don't know if you know what I mean by that. For a trash can, is there a trash can even in the room? Oh yeah, here's one outside the door. You just hate seeing trash on the floor, so it's a little distracting. Okay? Well, back at that time, the people who owned land were the landed gentry. They usually had some connection to some way in the past ruler or somebody that they had done favors to, and they'd given them land. Because technically all the land was sort of supposed to belong to the king, but he couldn't manage it all, so he had his lords and his earls and his knights and other people, they were the ones who owned land and they had the wealth. Okay? The common working people, they had been serfs or peasants, working for the big landowners. But about this time, you were beginning to develop a middle class. Industry was coming, and people who worked real hard and smartly were able to make some money. And once there was more money around, soon the landed gentry weren't controlling all the power. And some of the people who made the most money were sort of like the sin taxes, okay? Especially those who made alcohol. And James Prescott Jewell's dad was a brewer, so he made beer, okay? And he was pretty good at it, and he got very wealthy at it, okay? But the lords and the gentry and stuff, they looked down their noses at these nouveau riche, the new people. They didn't want to deal with them. And usually they weren't able to get as good of educations and things like this. But this kid, James Prescott Jewell, his dad had plenty of money, so he could hire tutors. Okay? So James Prescott Jewell got a great education. Now, part of the reason for that, he was a sickly child. In fact, some thought that he may have had hemophilia. Y'all know what that is, don't you? Free bleeders don't have enough platelets in the blood, so if you get cut, you could bleed to death, because it's not going to clot like it's supposed to. So he had to be very careful and couldn't work in the brewery, so his dad hired tutors, and he was a sharp kid and a sharp young man, and he soon was running circles around anybody else. Well, one of these lords was also a very good scientist, which is really unusual. His name was William Thompson, but his title was Lord Kelvin. And Lord Kelvin recognized the brilliance in some of the things that James Prescott Jewell was doing, and he introduced him into the Royal Society. They didn't want to have anything to do with the brewer's son, but they couldn't fight against Lord Kelvin. He had the honcho, so they had to let him in, and he really did well, and he was well recognized. If it hadn't been for Lord Kelvin, his work probably would have gone unnoticed, and we would have been far further behind. So that's what the unit of work is, and the SI unit is the joule, which is a Newton meter, and the U.S. customary force is pound, displacements in feet, so that's called a foot-pound. That's the only name we have for it. Okay, I did way too much talking on that one. Do we have time for an example? Maybe one. Sorry, I didn't realize we were running that much out of time. Let's see if we can do this first one. Find the amount of work done by a worker lifting 225 newtons. So let's see, I don't think we have a picture of this. So 225 newtons, what's that a measure of? And you say the worker is lifting 225 newtons of bricks. What's that a measure of? Say again? I can't hear you. No, what unit is it measuring? I mean, it's in newtons. Newtons are units. What is that measuring? 225 newtons of bricks. Newtons measures forces, right? And which force is this? Weight, exactly. This is the force due to weight. Okay, that's how the book does it. 225 newtons of brick. He's lifting them to a height of 1.75 meters. He's lifting them up onto his shoulders. This is one strong dude here. He's lifting them 1.75 meters. I'll tell you about what that is. I'm maybe a tad over 6 feet tall, and a meter is just a little bit more than a yard, so I'm just under 2 meters tall. So I'm 2 meters. That would be another meter probably above me. So this is about a 3 meter room that we're in, approximately. About a 10-foot ceiling. That's pretty close to 3 meter room height, okay? So he's lifting it up almost his height. So he's got it up here on his shoulders. That's the 1.75 meters, okay? So find the amount of work. 1.75 meters, that's his displacement. The displacement of that chunk of bricks, okay, the pallet of bricks. 225 newtons of bricks. That's the weight of the bricks. He's lifted it 1.75 meters. How much work did he do?
394 newtons.
The weight is equal to force, which is 225 newtons, times the displacement, which is 1.75 meters. Multiply those two together. And by the way, this is a multiplication problem, right? You can set up your circles or your triangles, put work on top, force times displacement down here. If you're looking for force, work divided by displacement. If you're looking for displacement, work divided by force. Yeah, so it'll work that same way as it did before with alpha equal ma. Okay, got your calculator? I can't do that one in my head. That's going to be something a little bit more, right around upper 300s or around 400. Huh? 394. 394 what? Newton meter would be one perfectly good way to express it. Or if you wanted to use another unit, 394 joules. Joules. Think those diamonds, though it's not spelled that way. 394 Newton meters or 394 joules. Okay? I think that probably took us just about to the limit, didn't it? What's the time? 6:20 what?
6:29.
Oh, okay. I don't think we got time for example 2, do we? All right. Sorry, I talked too much. Okay, we will pick up next time with example 2. Let's see if we did enough for you to get any homework exercises here. Oh, here's some. I think you could do number 1. They don't list 3 and 5, the numbers, but they're right there. The 2 givens underneath this is on page 206. Page 206. 1, 3, or 5. I think you can do those. Okay? I think maybe you can either do 7 and possibly 9, maybe 11, and we'll stop there and pick up the rest of those next time. Okay? Good deal. This is on pages 206 and 207. Are y'all in touch with Haley at all?
I can call.
Okay, well, I just say if you do get in touch, tell her that we will have class on Tuesday, but right now we're guessing not on Thursday, just because of my eye surgery. Haley.
You can send her a picture of the test so she can start working on it?
Either that or I could, or that would be good if you would. Or if she doesn't want to do it that way, she can just do it, pick up one on Tuesday. So whichever you want to do. Take the picture of it before you answer them all, though, okay?
Oh, yeah.
Okay, I'm just kidding. Okay. All right. Okay. We started in 5-4. So I'm going to shut this down. Is that okay?